But our method is not a true reproduction of what's happened in nature, but an approximation. We have an approximation that will make it work. So that is the state of the best simulation of nature we can do. Imagine if you have a quantum computer, then you don't need these approximations. You just put it in the computer, boom, it will come out. Under certain initial chemical conditions, you have a right-handed poison, and under slightly different conditions, you're going to get a left-handed beneficial medicine. So the simulation is a very powerful tool. It's also a big business. So if you have a quantum computer, you would have these wonderful things that you can do. So the simulation actually, there are different ways of doing it, so we don't put it under the same thing as a quantum computer. The other thing is that the people like, and therefore it's also big business, is games. One of the biggest thing now, it's bigger than books, is the publication of new games, of computer games. Well, because the description of a state is different, and it's probabilistic. It's like always having this gambling element in your game, which is a very complicated in a way, but it gives you rules. So I'm pretty sure that there's a small portion of the class, if I teach them these rules, and if I can make the games interesting, which of course I cannot, but that these people will make games. So if you can make quantum games with new rules, I tell you, you think, so there will be really, people would spend all their time. You think the kids are now spending a lot of time playing computer games. When you have quantum games, they'll be spending all their time playing the games. This list it's really just a very small corner. There are things we can sense that there are things that we just haven't been able to think about. So it just takes somebody with a brilliant idea to find a new set of avenue of applications. So this is why it's important. Some of it, like cryptography, is commercialized already. Quantum computing is still very far away, but we are making little digits. There is a government-funded program with many people working on different things. We meet once a year. And in 12 years, I find amazing how my colleagues have progressed. But they're not, we have no product to show, but it's a really interesting field to have. So this technology really comes out of knowing quantum theory well. So now, one of the things you do is you're just changing the way you think about things. So I'm trying to give you an idea of how just from that little thing of two different states, things can change. Why maybe this thing is going to work. This is the classical machine. It's called fuel injection. That's a little gadget that gives you, well, fuel injection. In an old-fashioned car, what do? You put your foot on the pedal, gasoline comes out into the chamber, got fired up, engine, the car goes, right? And there's not much control. So if you're heavy-footed, the car went boom, shooting out, and then you let it go, oh, it stopped. The car is very smooth nowadays. It's because you have a fuel injection device. Well, what is the principle of that? It's basically a computer. You have lots of little computers called microprocessors in the car. What it does is that it measures. It's like an internal speedometer. It measures how fast the your piston engine is going, if you like. And then it adjusts the speed. So the important thing here is it actually measures. And then it feeds the information back, and it then overtakes your pedal in injecting the fuel. So you have an injection, automatic injection, so the car is very smooth. You might be pressing the accelerator very abruptly, but the car goes off very smoothly. It smooths out your performance. There's a quantum mechanical equivalence of that. What I now want to tell you is the second idea. You have a state. Any machine means that you got to move that state from one state to the other. So that's a quantum operation. Now, again, it was parallel processing because when we move an arrow from one place to the other, we are moving both possibilities. So that's nice. But what if you make a mistake? Or what if it's moving too fast, you want to slow it down? Well, you can make a measurement. Now, the problem with this measurement is that it would only give you now the possibility, the individual. Once you toss the coin, it's not a linear combination of heads and tails anymore. You either get heads or tail, all right? So we call that a classical state. So when the quantum coin lands on the table, you get a classical state. So then you can tell if it's wrong, you can start over again. You can correct it, and then you feed it back. And then it goes, you can make a loop just like this, the feedback loop. But so it goes from quantum to classical, classical, quantum, and back and forth like this. You're mixing now classical state with quantum state. It's inefficient. A lot of us been doing it. I showed this because it was just completed a couple of months ago, a thesis of my student. And he said, well, he was actually an engineer. He worked in circuit design for a while, so he used the classical idea to do quantum. He said, well, I can design this thing where I don't need this. I just do it all completely quantum mechanical feedback loop. So it's not at all like this. So I say, oh, but it's like a steam engine governor. So historically, this, of course, steam engine works way before the car. When you have a steam engine, how do you govern the speed? There's a very interesting gadget. And you cannot imagine having to have a, they don't have electronics. Now maybe they don't use this anymore. But in the days, they have a governor. What is a governor? This is a stick, if you like. On the stick is tied. This is a switchable arm, so this angle can change. And this is two weights here to balance each other. You spin that rod with this thing tied to it, and the spinning rod is geared to the steam engine, piston engine, if you like. So when the piston engine go back and forth, this thing go round and round, this will go round and round.